Hello everyone and a very good day. My name is Govind Maniam from the Institute of Microengineering and Nanoelectronics, University Kebangsaan Malaysia. For the Student Research Day, I'm going to present my project titled Air Gap Optimization in Non-Contact Rotating Triboelectric Nanogenerators, a 3D COMSOL simulation. I will be showing my simulation model that I have developed to identify the proper durability and also the maximum output that we can get from the rotating tank devices. In the world we live in today, IoT is playing a big part of our life, and we are powering up all these IoT devices by using batteries. So researchers have come out with a way to overcome this issue of replacing batteries by using energy harvesting systems. Among all these energy harvesting systems, we have been looking at triboelectric nanogenerators, which are also a promising way to generate electricity with ambient energy. There are 4 working modes in a triboelectric nanogenerator. The first is vertical contact separation. Second is the lateral sliding. Third is the single electrode mode. And also finally, the freestanding mode. For my work, I have chosen the freestanding mode, as this mode is very suitable to be used to harvest energy in a rotating motion. This brings to the problem statement of my work. Why are we in need to do a simulation for a non-contact rotating triboelectric energy harvester? As of now, most of the triboelectric nanogenerators are working in a contact-based solution. So all the 4 methods that I have mentioned before are working in a contact-based solution, especially rotating-based triboelectric nanogenerators. So this causes a lot of wear and tear into the device and also will increase the frictional heating and also progressive degradation of the material. To overcome these problems, we can introduce an air gap into the rotating based triboelectric nanogenerator. This will increase the durability of the device, but however, the output will be quite low. However, durability is a big issue in triboelectric nanogenerators, as most devices don't last even for a few cycles. So, increasing the durability is very important in these rotating based triboelectric devices. So, rather than spending so much money to build a prototype, we will be doing a simulation to find out the best solution. Now, we will see the architecture of the tank that I will be modeling. This is the device that I have modeled. A rotor with 6 segments made of a nylon called polyimide 11, a stator assembly below it with 12 electrodes coated with PTFE. For this experiment, I have fixed every other parameter: the thickness, the electrode gap, the area. Only one thing changed in my study: the air gap, which I will sweep it from 0mm to 8mm. To study this, I have built a 3D finite element model on COMSOL multiphysics. I will be rotating the rotor for 360 degrees and record all the outputs that I will be getting. And here are the results. This is how one rotation looks like. At 0 degrees, it's perfectly balanced and there is no output. Rotate 30 to 40 degrees, the charges lift and there is a voltage. Across 45 degrees, the polarity will flip. From 50 to 60 degrees, the voltage is now reversed. This is back and forth exactly what generates an alternating output. And here is the key results. As the air gap widens, the voltage drops steadily. At 0 gap, it peaks near 900 volts. By 8mm, it's almost flat. The signal is gone. The charge density tells the same story, from over 16 microcoulombs per meter square at contact down to 1.3 at 3mm and basically 0 at 8mm. At that point, the stator and rotor are not charging any electricity. So, what is the proper air gap? In my study, I have figured out that 3 to 5mm is the proper air gap that is enough to eliminate the friction completely, and it is also narrow enough to keep the output strong, around 530 to 650 volts. So what can we conclude? To get a proper output from the non-contact rotating triboelectric nanogenerator, we can use an air gap from 3mm to 5mm. This gives a very good durability to the device as well as a very good output from the device. The model that I have developed can be used for other researchers as well. We can change the material, we can change the electrode gap and also other parameters. So this model works very well. We can use it to identify air gaps and maybe dielectric thickness soon. To further this study, I can build a prototype to verify the results that I have gathered from the simulation. That's all from me. Thank you for watching.